The work I'm going to present is motivated by two observations and one following question. Namely, first observation is that time and resources are quite important if you want to handle real-world planning problems. And the second observation is that in general, at least in sequential planning problems, heuristic search is quite an effective approach, obviously. And in particular, if combined with the context-enhanced additive heuristic to guide the search. And we focus on the context-enhanced additive heuristic here because we believe that it might be quite easily extensible to the temporal and numeric setting. So the question we wanted to answer is, does this whole heuristic search approach work well if we have to deal with time and resources? Now, let's just consider a tiny example. We have two robots, robot 1 and robot 2, which can move between three locations depicted here, where the tasks these robots have to perform are some kind of gardening tasks. They have to water flowers at these locations, L2, L1, and so on. And first of all, the temporal aspect comes in because the iterative actions walking between different locations have durations that correspond to the distances. Watering actions have durations that depend on the water levels. And of course, we also have a numeric aspect because these water levels are real numbers. And one important point concerning the temporal side is, of course, that the robots can work concurrently. So, for instance, robot 1 could walk to the left, do everything that has to be done there, and robot 2 might move to the right concurrently and do his job there. So, I think you've seen in the last talk how these iterative actions, what they look like. So we have durations, start conditions, persistent conditions, end conditions, and also effects at start and end points. And these conditions, as can be seen in this water action here, can also involve numeric variables. For instance, the start condition Wi has to be greater than or equal to nk minus hk, or we may also have effects on numeric variables, assignments, decrements, and so on. Then the resulting plans, they have to, of course, respect the causal dependencies as always, and temporal constraints as well. And they may contain concurrent actions, like in this example here. The upper row of actions is just what robot 1 could do on the left-hand side of the example you saw, and the lower line is what robot 2 would do on the right-hand side of the example. Now, let's become a bit more formal. We consider temporal and numeric planning tasks with multi-valued state variables. So we have a finite set V of state variables. They can be either numeric, so their values are real numbers, or they can have arbitrary finite domains. And so to simplify the presentation here, we subdivide these variables into comparisons between the results of comparisons between numeric variables and all the rest. And as usual, we have an initial state, we have a goal description, we have a set of axioms, and we have a set of durative actions. I mentioned the durative actions already, but I guess I should tell a little bit more about the axioms, because often they are not directly encoded in the planning task you get, but rather a result of compilation, as it's also the case in our system. So most of the axioms we have to deal with are just the result of compiling away numeric or logic subterms. In particular, this allows us to share subterms that occur in several preconditions or effects, and it will be later also convenient to for the heuristic computation. So this is just a small example. We have this condition here: W minus n has to be greater than or equal to 0, and some other condition. On the right, you see the path tree, and obviously the leaves of this tree are just the atomic variables, and you can introduce auxiliary variables for all the interior nodes and axioms corresponding to the edges. So axioms saying that auxiliary variable aux1 is just the difference between w and n, and so on. Now, just a little bit about our implementation of our system. We extended the fast downward planner by Helmut and Richter, and actually, at least on an architectural level, our planner follows fast downward very closely. So in the first step, we translate PDDL to temporal and numeric SAS+. Then there's a pre-processing step. And finally, in the third step, I want to focus on, for the rest of this talk, the actual search is performed. So the main features of this search is best first search. It uses deferred heuristic evaluation and preferred operators. And as I already mentioned, it is guided by an extension of the context-enhanced additive heuristic. Now, the elements of our search space are so-called time-stamped states, consisting of a timestamp that just says how much time has already elapsed since the beginning, a state, that's to say, evaluation of the state variables, and information about the actions currently under execution. That's to say, which actions are running, which persistent conditions still have to hold, which end conditions will have to hold, how much time is left until these conditions have to hold, and similarly, which effects still have to trigger in the future. And the two types of search space operations are, first of all, inserting an applicable action at the current time point, where applicable means that it doesn't interfere with any other of the actions already scheduled. Or, second possibility, we might advance the current time point to the next scheduled happening. Before going into the details about how the context-enhanced additive heuristic is implemented, and in particular how time and numbers are represented there, I want to just briefly sketch the idea of the heuristic. And the idea is, first of all, we try to solve the top-level goals and then recursively take care of sub-goals or preconditions. And so we end up with a makespan estimate by just accumulating costs of these transitions in domain transition graphs. In addition, we need to keep track of local contexts of the nodes in the DTGs, so that we know what side effects previous actions had. So on the one hand, there are some drawbacks of this heuristic, in particular in its inadmissibility, which results first from the fact that we potentially get repeated solutions to the same subproblem and count them multiple times. Second, our transformation to instant actions, I'll mention in a few slides, can introduce double counting of durations. And most importantly, the heuristic isn't really concurrency aware, but you will see this in a moment too. On the other hand, we have this huge advantage, namely you get preferred operators as a very, very cheap byproduct of the context-enhanced additive heuristic. And you can use these preferred operators later on to prune the search, or at least to guide it towards using the preferred operators first. Now, as I said, we need these instant actions because these durative actions are too complicated, have too complicated a structure to efficiently reason with them within the heuristic. So we ignore this start end distinction and end up with instant actions just consisting of preconditions, effects, and a cost value. The first way of coming up with these compressed actions is similar to this TGP semantic. So we collect preconditions, we collect effects, and later on just say we may transition to say value C if conditions A and B are satisfied and do not care about any interactions between start and end. And moreover, we interpret durations as costs here. So this duration 17 becomes the cost of the compressed action. Unfortunately, compressing actions in a pre-processing step is not alone is not enough, because well, just consider this example here. We have an action that gives us as an end effect a goal we need to achieve, and it deletes its own precondition. And let's also assume that there is no other action available that would restore this precondition A again. And assume that this action is already scheduled. Say 7 of these 17 time units have already passed at the current time point. Then the heuristic computation would consider this temporal state at that end, because the compressed version of this action would not be applicable anymore. So in this particular case, we have to introduce extra weighting transitions for these kind of actions that are already scheduled without any conditions, with the effects the uncompressed action has, and the cost is the remaining time of the action already scheduled. And finally, axioms become instant actions in the obvious way. They basically are instant actions already. And now if we want to reason with these instant actions, we fall back to, well, I should explain it on an implementation level. So we need so-called local problems here. And the local problem for one variable just answers the question, how costly is it to change the value of that variable from one value to a different one? And let's say this is the causal graph of our problem. One goal variable here with just values false and true. Two other discrete variables L1 and L2, a comparison C, and 4 numeric variables N1 through N4 here, where this part just corresponds to these comparisons and to the sum here. And now we want to make G true, whereas in the current state it is still false. So when traversing the causal graph, we start with G, go into the DTG of this variable G, and try to take this transition to the value G equal to true. But this transition is conditioned on L1 being W3 and C being true, which is both unsatisfied yet. So L1 is W1, C is false. So we cannot take this transition immediately. If we could take it, we could take it at a cost of 10. That's the cost of the transition. But as I said, we can't. So we have to go down in this causal graph and take care of variable L1 first. Now all the transitions here in this DTG are unconditional, so we can take them one after the other, and finally end up here at W1 equal to L1 equal to W3, which is exactly what we needed here in this precondition. So half of the precondition is satisfied, and we can take care of this comparison C. C is true by definition if and only if N3 is greater than or equal N4, which is false currently, but we could take this transition if it were true. And when is it true? Well, of course, if we either decrease N4 or increase N3. In this example, decreasing N4 is not possible, it's just a constant. So we are left with trying to increase N3. N3 is the sum of N1 and N2, so we have to increase either one of them. And now if we follow the edges back here, we see that increasing N1 is again conditioned on the value of L2. Changing the value of L2 is conditioned on C being true. And, well, we tried to make C true already, so that's the wrong way. And we are left with trying to increase N2 finally. And this actually works. We have this transition here at a cost of 5 that increases N2 by 10, which is enough. This makes N2 15. Propagating this value up, N3 becomes +5. This propagates up to C, which becomes true. And finally, we may take this transition in DTG of G, making it true. And the cost we have accumulated along the way was 20. 15 for this transition here, and 5 for the transition here. Now, as I said, we implemented this approach on top of Fast Downward, and we compared it to 5 other temporal planning systems from the last 2 competitions, and we compared it on the benchmarks from 2008, also using the evaluation scheme from 2008. So each planner gets 1 point for each solved problem, weighted with the solution quality. So we had a 2 GB memory limit, 30 minutes timeout per problem, and every planner was allowed to use anytime search. So we just counted the best solution found after the 30 minutes. And that's what the results look like. So in every domain, there were, I think, 30 problems. So each entry here must be a score between 0 and 30. This is the baseline planner, FF plus rescheduling, Crikey 3, LPG, SAPA, SG plan, and our system here in the last column. And as you can see, with 148 points, we slightly outperform LPG and the others by more or less larger margins. Maybe the model train domain should have been taken out here because some of the planners weren't able to solve it, and we ourselves only got 1 point. But at least 2 planners managed to get some points. But still, even if we ignored this domain, we still probably would have been slightly on top of LPG. But what we found out when we had a closer look at the results was that the reason for this rather high score was not so much that we solved many problems, but rather that the solution quality was rather high. And to see this a bit more clearly, we performed another set of experiments where we compared our average solution quality to the average solution quality of other planners, always on the set of problems solved by both planners pairwise compared. So, for instance, here, this entry means on the 18 group planning problems that both baseline planner and TFD solved, the solutions of the baseline planner were on average 14% longer than ours. And all the blue entries here mean our solutions were more or less shorter. As you can see, that there are a few entries where the competing planner was better. So LPG found better plans in the park printer, transport, and woodworking domain, but averaged over all instances, our make plans outperformed those by all the other planners. And the reason is fairly clear. It's a forward search, and we greedily insert actions, so you have to expect to get rather small plans. And another important point here is that the preferred operators also lead us to quite good plans very early. So to summarize, we implemented a temporal and numeric planner that used forward search in the space of time-stamped states. It used the heuristic guidance by an extension of the context-enhanced additive heuristic, and is at least competitive with other approaches to temporal planning, no matter which other approach we look at. And in particular, the plan quality is rather high. And future work includes making the heuristic concurrency aware. This is a large problem we currently have to deal with. And the relaxation of the numeric features within the heuristic is also quite rather strong, and we could use a weaker relaxation probably. Okay, thank you. you have to distinguish between what happens within the heuristic and what happens within the search. The heuristic doesn't consider such things, but the search itself can find some plans. For example, this light match thing can be solved by our planner. Yeah.
So, although it's true that you're planning to find a solution to the light match problem because you added one more point into the space between the current point of execution and the next event sample, you don't consider other time points in there. So there are many problems you could solve.
Correct. Yes. The only reason why we solved this particular one was because of the epsilon. Yeah. Exactly. Yeah. Yeah.
I was interested that you said that you thought maybe you should remove the model frame you made because not many planners can solve it. But I think that that's just as interesting as the other domains that you can solve. So what I'd like to know is more about the model frame domain so that it can be depending on detail. It would seem a strange thing to do to simply disregard
Yeah.
the shot planner in a good light.
Yeah, I didn't mean completely disregard it. I just was afraid that it could raise the impression that, for instance, this domain would have been responsible for our high score because we scored, yeah. Uh, 30 minutes. You have this mode where you can say how many solutions you want, right? And we set this to a very high number, then gave LPG the whole 30 minutes, and then used the best solution.